Hi, pre-calculus. There are a couple more problems we are going to do today. These are totally optional. Don't feel like you have to, but if you did try them and you want to see the answers, here we go. All right, so it says use the function to answer each question, use infinity, negative infinity, or does not exist, when appropriate. So we're going to start with f of 0, meaning what actually is the function equal to when x is equal to 0? If I look, this has a hole, okay, so it's not 2. And I look on the left side, there's really nothing there. What does that mean? F of 0, the solution would be does not exist. There is not an answer here. What about f of 2? This is literally what is the point when x is equal to 2? So that's this point right here, meaning the answer would be 0. F of 3, what is the function at x equals 3? Well, we see that there's a hole here, not that. There's a hole here, not that. But hey, it's this point up here. F of 3 is equal to 3. Next one, limit as x approaches 0 from the negative direction of this function. So I'm coming at 0 from the negative side, and I'm just going to follow my function, and I see what is my y approaching? Well, it's technically approaching negative infinity, but we also know that infinity does not actually exist. It's not a real thing. It's a construct of our minds. So therefore, that's what those 3 dots are, does not exist. What about the limit as x approaches 0? Not from the positive, not from the negative, but as it approaches 0. So on the left, we said that it approached negative infinity. On the right, it's approaching 2, because negative infinity is not equal to 2. This limit does not exist. All right. What about the next one? The limit as x approaches 3 from the positive side. So we're looking on the right of it, and I'm following. My y value is approaching 2. The limit as x approaches 3, okay, so again we have to look at from the left and from the right. Because they are not coming to the same thing, we're coming up to 1 and 2, this limit does not exist. And last but not least, the limit as x approaches negative infinity. So now we're looking as x gets close to negative infinity, what is my y getting close to? If you notice this dashed line, that's kind of suggesting, hey, there's an asymptote right here. Where is that asymptote? The asymptote would be at 1, so this limit is equal to 1. Next problem, solving a limit algebraically. So this first one, limit as x approaches 0 of the following function. So we look at what we got, and our first step is always just plug in that value. So we got 0 squared minus 25 all over 0 squared minus 4 times 0 minus 5. If I simplify, I get negative 25 all over negative 5, or a final answer of 5. Because we got a number, we are happy and we're done. What if, though, we have something different? All right, what about this one? Same function, different limit. So the limit as x approaches 5 in this case. Okay, we're going to start the same way. We plug in 5. So 5 squared minus 25 all over 5 squared minus 4 times 5 minus 5. Uh-oh. On top, we're getting 25 minus 25, which is 0. On the bottom, we're also getting 25 minus 25, which is 0. This is that signal that we need to do more work. What's the more work here? More work. Because we have a polynomial on top and on bottom, that's a pretty good hint to say that we are going to have to factor. So we look at the top, x squared minus 25. I recognize that as the difference of squares. So we have x minus 5 times x plus 5. That's my numerator. All over the bottom. So I look at this and I see that I need to multiply to get to negative 5 and add up to get to negative 4. So that's going to be x minus 5 and x plus 1. We're happy because, look, we have a common factor here, x minus 5. We can cancel those. We are just left with the limit as x approaches 5 of x plus 5 all over x plus 1. And here's the good news. We can now plug in this 5. 5 plus 5 is equal to 10. 5 plus 1 is equal to 6, and get a final answer of 5/3. Yay! Next problem. So this one is something we haven't quite seen exactly the same thing, but a lot of the concepts that we've learned so far are included in this problem. It says, answer the following questions for the piecewise function defined as we have on this right side. So here's our function. Now, it's kind of a weird function, right? F of x is equal to sine of pi times x for x is less than 1, and 2 to the x squared power for x is greater than 1. I repeat, do not expect you to know what this looks like graphically. In fact, you shouldn't need it for this problem. We have three things. First, they ask us for f of 1. What is this function when x is equal to 1? So we go over to this right side where we're looking at the constraints, and we notice it has x is less than 1, x is greater than 1. There is nowhere that this function is defined at 1, which means what is f of 1? It does not exist. It's not defined on this function. All right, then we look at our limits. So we have the limit as x approaches 0 of f of x. If I am approaching 0, I am going to be focusing on this part of my piecewise function. Why? Well, 0 is, sorry, that you can't really see that. Let me try that again. All right, 0 is less than 1. So that means I'm going to be this part of my piecewise function here. So the limit as x approaches 0 of my function is equal to sine of pi times 0, or sine of 0. I'm thinking about my graph of sine here, so I know it looks like this, right? What is sine equal to at 0? It's equal to, well, 0. That is my answer for B. All right, sorry, I cleaned that up a little bit. Now let's look at C. So C, the limit as x approaches 1 of this function. So we know that x doesn't actually exist at 1, but we can still look at what is it approaching as we get close to 1. So to do this, we need to take two limits. The limit as x approaches 1 from the positive side, and the limit as x approaches 1 from the negative side. So if we're looking at the positive side, that means for x greater than 1, so in this, we're going to use the sine of pi times x. Here, x is approaching 1 from the negative side, meaning x is less than 1. This is where we're going to use 2 to the x squared power. Again, because this function is defined as two different things depending on these values here. So let's evaluate both. Let me just extend the page a little. Oh, this thing is so hard. Oh, goodness. Okay, sorry. So if I want to evaluate it on this left or right side, excuse me, I'm pretty much going to do sine of pi times 1, which is just pi. Okay, sine of pi is 0, so I am approaching 0 from the positive side. Over here, I'm going to plug in 2 times 1 squared, or 2 to the first power, which is 2. So on the right side, from the positive direction, we are approaching 0. From the negative direction, we are approaching 2, because the limit as x approaches 1 from the positive side does not equal the limit as x approaches 1 from the negative side. The limit as x approaches 1 period of this function does not exist. Yay. Two more problems for you. Is the following function continuous? If not, what kind of discontinuity does the function have? All right, so we're looking at this. It's another piecewise function. The first thing I notice is that the most of the function is a rational function, this piece right here, the x squared minus 1 over x minus 1. So I'm going to look like this function when x is not equal to 1. Which is good because, hey, if we consider this function, we see it is the difference of squares all over x minus 1. And we notice that we have a common factor in the numerator and the denominator, which is a whole. And that's the place where we aren't existing here, okay? So that seems kind of weird, I realize, but basically, we have this rational function, and there's a whole at x equals 1, which is okay because we're defined everywhere except that. All right, so now let's look at the second piece. The second piece is 5/2 when x is equal to 1. So is the following function continuous? Right now, we're not actually sure. In order to determine if it's continuous, we need to see what is the limit as x approaches 1 of this function. So x squared minus 1 over x minus 1. We already have, sorry, I'm losing focus. We have already done a lot of the heavy lifting here by factoring the numerator and the denominator. So we can simplify, because if we plugged in 1 here, we'd get 1 squared minus 1, 1 minus 1. We would get 0 over 0, which means we have to do more work. So we're doing more work right here. Sorry, I skipped that. I'm doing a bad job right now. Okay. 0 over 0, we need to do more work. We factor the numerator, canceled out the common factor, and we get 1 plus 1. We get that the limit is 2. Meaning this function, I don't know exactly what it looks like, but I do know this. At 1, it is approaching 2, but it has a hole. I know my function probably looks something like this. It has a hole at x equals 1. It is approaching y equals 2. And now the question is, does the original function plug up that hole? Does the function actually define something here or not? That's the question. So we look at what the original function was. Here's our original function. We see that it has this hole at x equals 1. And we see that it's not plugging the hole at 2, it's plugging the hole at 2.5, or 5/2. So is this function continuous? No. It has a removable discontinuity. Removable discontinuity. All right. And then the last question is extend the definition to create a continuous function. Well, good news. We pretty much already did this. We can keep the top as is. X squared minus 1 over x minus 1 when x is not equal to 1. And what we just said is in order to plug up this hole that exists when x is equal to 1, we need the y value to be 2. So that's all we need to change. We have now extended the function to remove that discontinuity. Hopefully that was helpful. I realize I kind of did a very bad job of explaining that last thing, but hopefully it helped. Otherwise, please reach out. Let me know if you need more help. Miss you guys.